Today is the first day of the 5th week. So, we started looking at the pulsing technique called mode locking, and there we looked at the basic principle of mode locking. So, what we said in the previous class, let's have a quick recap of that. So, we said that a particular cavity can host several different frequency modes, particularly longitudinal modes, and all these different longitudinal modes can, if they are not related in terms of their phases, which generally is true, in that case we have a situation where we get an output which is totally chaotic. So, only you get random fluctuation of intensity, and it appears to be like a continuous wave laser and with a very low intensity due to destructive interference, because their phases are not correlated. In case if these modes are correlated in terms of their phases, meaning that neighboring modes are all somehow locked in their phases, that means they are not haphazard, they have a particular relation and that relation maintains, then you will get a single pulse with high intensity because of constructive interference at that particular region, and everywhere else there will be destructive interference. So, you will have only one peak coming out of all these modes, and if you can generate a cavity such that it houses only one such peak, then that particular pulse will move back and forth between the two end mirrors and it will give an output through the end coupler. And we also showed that these type of pulsing technique can yield really short pulses with really short width or short time duration, and we also estimated like based on a particular active medium for which we know the bandwidth, spectral bandwidth, and with the cavity length, how much we can compress the pulse, that means how short we can go in terms of its width. And we also said that the width of the pulse is related to the number of modes within the cavity. Now, if we tell it very explicitly, then actually it is dependent on the bandwidth, spectral bandwidth of the active medium, because a cavity can support infinite number of modes, okay, but how many modes are there corresponding to the given bandwidth of the active medium, that is what will ultimately be useful for us. Anything outside the bandwidth of the active medium is not of our interest, okay. We are interested only on those frequencies corresponding to those certain longitudinal modes which fall within the envelope of the spectral bandwidth of the active medium. So, therefore, it is the pulse width essentially dependent on the spectral bandwidth of the active medium, right. That is what we boil down to. So, now having said that, let me ask you a question. If I take some gaseous system as my active medium for my laser, say for example, like if I take nitrogen laser and I take a dye laser, okay, say for example based on say rhodium dye, which one of them can give extreme short pulse like we calculated in the previous class in the order of few frames per second? Is it both of them or one of them or none of them? If you think about this question properly, then you will understand that the spectral bandwidths are not the same for a gaseous system and a dye, organic dye most likely, in some solvent, that is active medium for a dye laser. There is heaven and hell difference in terms of their bandwidth. So for a gaseous laser, say for example helium or nitrogen, their bandwidths are extremely narrow, so that they can support 1, 2, 3, 4 number of modes. On the other hand, this dye laser emission bandwidth, the dye emission bandwidth essentially is so large that they can accommodate 10 to the power 3 to 10 to the power 4 number of modes. So immediately it is clear that a gaseous laser mostly, they cannot under any circumstances give rise to ultra short pulses. At max you can get like a nanosecond pulse. Okay. On the other hand, these dye lasers or some certain solid state laser, for example like titanium sapphire laser, there you can have a spectral bandwidth which is large enough to accommodate a huge number of modes, and we know that more the number of modes, more is the possibility of shortening or compressing the pulse. So I can achieve extreme short pulses with a solid state TISAP laser or a dye laser, say a picosecond to femtosecond pulse, but not with a gaseous laser like helium neon laser or nitrogen laser for that matter. Okay, so we have understood what is the basic principle behind mode locking. So we need to really lock the phases of the different modes. Now the question that we have to ask now, that fine, I understand the basic principle, but how to get it, how to achieve the mode locking? Or in other words, if I ask the same question in a different way, is that how to create a situation with a fixed mode to mode phase relationship between the neighboring modes, exactly what I was talking about. Okay. So the answer is there are several different ways to achieve this mode locking. Okay. Now doesn't matter how many different ways you have, the principle, okay, the basic principle is going to be the very same, it's not going to change. Okay. So what we have to do, we have to achieve the periodic modulation of the optical resonator parameters, something like amplitude or frequency, with a frequency equal to the difference of the two neighboring longitudinal modes. If I can achieve that, that's it, I can lock the phases. So that's my target. All right. So there are mainly two different types of mode locking that we can achieve. One is active mode locking and another is passive mode locking. Okay, so we will talk about these things in bit detail. We will try to understand how exactly this is done experimentally. Just for your information, within the passive mode locking, there is something also known as self mode locking, which happens due to the self focusing of the laser beam in the cavity. Okay, so if time permits, we can also touch upon that particular thing. So in case of active mode locking, what you do, you control some parameter from outside. Okay, so you control it. Okay. In case of passive mode locking, you put something which decides how to get that mode locking and when to do that. Okay. So your control over this mode locking conditions will be removed. So this is known as passive mode locking. Now as we said in the last slide, that the modulation of optical resonator parameters will be needed so that you can lock the frequencies of two neighboring modes by whose gaps are equal to C by 2L. So the modulation of this optical resonator parameters with the frequency delta omega q the modulation of the optical resonator parameters with the frequency delta omega q, it can be obtained by varieties of methods. Okay, so what are those methods? For example, you can use an acousto-optic device which produces sound wave. This is not totally new to us. We have seen in case of Q switching and cavity damping how an acousto-optic modulator is used. So this acousto-optic modulator or acousto-optic based device can modulate the laser beam's intensity propagating through a resonator, and in that way we can achieve a mode locking. Also, we can use, instead of acousto-optic modulator, we can use electro-optic modulator, which are driven at exactly the same frequency as that of the separation between two longitudinal modes, which we write as delta omega q. Okay. So we know what is that? That is C by twice L. L is the cavity length. And also we can use saturable absorber, which we have also learned in case of passive Q switching. So we can use a saturable absorber which can modulate the amplification factor of an active medium. So the first two, that is A and B, they belong to the active mode locking, whereas the third one, it belongs to passive mode locking. Okay. So these things are not very surprising to you. While discussing about Q switching, we also said that this active and passive techniques to achieve pulsed output is there in Q switching as well as in mode locking, and the similar kind of devices are used to achieve different type of pulses based on either Q switching, cavity damping or mode locking. So we will see how to do those things. Now we should ask that what is the mechanism which causes the randomly oscillating longitudinal modes to begin oscillating in synchronized phases under the influence of modulating factor, whatever that may be, at a particular frequency which is equal to the gap between two neighboring modes. Right? So what is that mechanism? That we need to understand first. So we can achieve this condition only when, that is phase locked modes, only when we have these modes in a coupled condition. If the modes are not coupled or correlated, then the result is a chaos. We have seen that right at the beginning of the class today when I was recapitulating few things taught in the last class. I showed that particular figure when the random phases in the longitudinal modes resulted in a total chaotic intensity distribution in the output beam. So if we want to avoid that, then I must have a condition when somehow these modes are coupled together, and later on we can bring in a condition where these are so coupled that they will give rise to a constructive interference at a particular place and elsewhere destructive interference, as we described in the previous class. So when we modulate either the amplitude or the frequency of a given longitudinal mode of frequency, say omega 0, small omega 0, with the modulation frequency say capital omega, an additional radiation component appears at omega 0 plus minus capital omega multiplied by n. Okay. N is an integer, it can be 1, 2, 3, anything. So if the modulation frequency omega is equal to the frequency gap between these two neighboring longitudinal modes, that is in our case what we said as delta omega q, then these additional components, that is this part we are talking about, that omega 0 plus minus n capital omega, these additional components overlap with the neighboring modes. This is very important. Okay, so you should note this part. If I can modulate the if we can use a modulation frequency such that the modulation frequency is equal to the gap between the longitudinal modes, then this additional bands, or we call it like side bands, will exactly overlap the neighboring modes, because my modulation frequency is capital omega, and I am choosing this capital omega to be equal to delta omega q, which is equal to c by 12, equal to the gap between the longitudinal mode. And I know that if I modulate with a frequency capital omega, then my main frequency, which is known as carrier frequency or the incident frequency, is going to be shifted by, say, capital omega or 2 capital omega or 3 capital omega and so on. In that case, these shifted side bands are exactly poised at the position of the neighboring group, because my neighboring mode, because my neighboring modes are separated by the same amount, c by 12, which is equal to now my capital omega. So this point has to be very clearly understood. So we are going to build the whole story based on this. Okay. So now, in that case, when this side bands or this so called additional components, they overlap with the neighboring modes, they cause the coupling of modes and stimulating oscillation in the same phase. This needs to be understood very clearly. I am allowing the creation of the side bands exactly in the positions of neighboring modes. So this is mode 1, mode 2, 3, 4, and I am selecting this mode 1 as my carrier frequency, that is small omega 0, and then I am creating omega 0 plus capital omega, which is at the next mode position. And if I keep doing that, so essentially all of my modes are coupled, because if I choose this particular mode to be my omega 0, then I can create the sideband at the position of this one. So in that way, all the modes are now coupled in terms of phases. So they will, if they propagate in the medium, they will create the same the photons with the same phase. So they will keep oscillating in the same phase. So let us now consider one particular mode that we talked about using acousto-optic device. How an acousto-optic modulator can bring in this particular condition where creating the sidebands at a particular frequencies which are exactly the positions of the different neighboring mode frequencies, and thereby causing a coupling between the neighboring modes, which will create the or which will stimulate the oscillation at the same phase relation. Exactly, that's what we want. Mode locking is all about creating a phase relation between the modes and maintaining it. That's all is mode locking about. Now, in case of acousto-optic modulator, this particular modulator, it generates sound wave. We have seen that in case of Q switching, and this sound wave modulates the amplitude of the laser beam. So what we are talking about here is the particular frequency that we are choosing as the carrier frequency. So if we target one particular frequency, say like 800 nanometer, so acting as a carrier frequency, and I can modulate that within the resonator, optical resonator in this particular case. So since we are going to use Acousto-optic modulator and we will be dealing with the sound wave, so therefore the understanding of the mechanism governing the interaction between light and sound wave is of utmost importance. And this Acousto-optic devices, as we have seen, is often used in laser technologies, and we have already seen this. Okay. We have already discussed. In cavity dumping or in Q switching, we use these things. Now, suppose I have a Acousto-optic transducer which is emitting an ultrasonic wave at a frequency capital omega, maybe a megahertz, and if I place that transducer in a glass of water. So take a glass of water, take your transducer which emits acoustic wave in the range of say 10 power 6 hertz and put it there. And you bring in, so suppose this is my glass of water, so you put your transducer here so that it can send sound wave in this direction, okay, downward. And you bring your laser light through this one, fine. So laser light is illuminating this whole water in the glass. So we take the laser beam frequency as small omega. Now if I do this experiment, what will I see? So this whole experimental thing is shown here. You have a glass of water and transducer is kept here, which is sending sound wave at frequency capital omega. So capital omega is for sound frequency, which is the modulating frequency, and our carrier frequency is the light frequency small omega. Now at this condition, what happens when I start sending the sound wave? This light frequency small omega, that gets split into several different beams, and at each side of the fundamental beam they are disposed, and not only they are separated in space, but they are also separated in frequency. So their frequencies are either upshifted or downshifted. So by an amount omega plus minus n capital omega. Capital omega is my modulating frequency coming from the Acousto-optic device in the form of sound wave. Fine. So this already we have mentioned that when this happens, when I modulate, it gets upshifted or downshifted, and of course when n equals to 0, you have the unperturbed incident light passing through the medium. Okay? So this I can show pictorially like this. So the unperturbed part goes as such, and in different direction they are split, having different frequencies. So this is the down shifted in terms of energy, and in this direction you have the upshifted. This particular effect is known as Debye-Sears effect. Okay, so this is after the name of the scientist, and this particular effect, if you think about it, is pretty similar to light diffraction at a slit, by a slit. Why? Because in case of light diffraction by a slit, if you remember certain experiments using these slits, what you see, one particular intensity at the middle, and then you see that there are dark and bright spots, regular spots, in both the sides of that main spot, and they are very much periodic in nature. Here also we are seeing the same thing. Only difference between a diffraction by a slit and this process is that in case of light diffraction, no change of energy takes place. You just see the intensity variation, right? So you see a maximum intensity at the middle, and then smaller intensity in both the directions, okay, which dies down. But there is no change in the frequency. But here, when I modulate with an active sound wave, we see a definite modulation of the light frequencies too, and that is in both the direction, upshifted as well as downshifted. Now we said that, okay, this is very similar to diffraction. I gave this analogy. So why is it so? See, sound is a longitudinal wave. So what it does, it just compresses and dilates, So it changes in the direction of its propagation, correct? So it creates different density region in the medium, and particularly this regions of dilation where it gets widespread, it can be treated as the slits through which more light passes than through the region of greater density. That clearly makes sense, okay. Now this is very good. It shows nice similarity with diffraction of light. We all agree about that one. But the question remains, why do the frequencies, say small omega plus minus capital omega, small omega plus minus 2 capital omega, and so on, why do they appear? That's a question that we need to answer. So let us imagine that light of frequency omega, it arrives at a medium characterized by a refractive index n1. So pictorially it is shown here. So this is my active medium, it's shown here. It has a refractive index of n1. Everywhere else, so apart from this active medium, everywhere else, suppose this refractive index is n0. Okay, so this is my environmental refractive index is equals to n0. Fine. So it goes through that active medium, faces its refractive index n1. Now, if the environmental refractive index n0 is less than that of the active medium, then what will happen? The light in the medium will travel slower by what amount? By an amount n1 by n0 amount. So the light will be retarded. Why it will be retarded? We have already seen this equation, right? So if you utilize that, you can easily figure out why. Now suppose for the time being we assume that we have some way of modulating the refractive index. So I have started with n1, I can go to n1 prime, n1 double prime, and so on. I don't know how, but suppose I can assume that I can do that, okay. So and I can do that with frequency capital omega. Now if I can do that, then what will happen? It will cause the light in the medium to propagate faster or slower. It will make some change in their the speed. and the output light from the medium will also be modulated. And what this will do, the output light is characterized by the carrier frequency omega, small omega, that is the incident light frequency, and a side frequency of capital omega, leading to the appearance of additional components of frequency at omega plus minus n omega. So this is the reason. Okay. So if I can really vary the refractive indices, so it will be leading to the creation of the side bands along with the along with the carrier frequency, and these side bands will have to be at frequencies shifted by n capital omega, because the modulation frequency is capital omega. So we will keep discussing this part in the following classes as well. So in the following class we will talk a little bit more about this one, and look at the possibilities of other techniques which can also give us mode lock pulses. Thank you very much.